Have you ever been stuck in a maze? You know that feeling, right? You try one path, you hit a dead end, and then you have to backtrack. Well, it turns out that really human instinct, it actually has a name in the world of computer science. So today, we're going to dive into something called depth-first search, an algorithm that is way more powerful than you'd think, but also super intuitive.
I mean, really, think about it for a sec. If I put you in front of a maze right now, what's your go-to strategy? How do you even start?
Yeah, that's what most of us do, right? You pick a path and you commit to it. You follow it all the way down as far as it'll take you. And when you hit that dead end, you don't just throw your hands up and quit. Nope. You just retrace your steps to the last fork in the road and try a different way. It's simple, but man, is it a powerful strategy.
Well, guess what? That exact strategy, that very human way of exploring a maze, has a fancy name in computer science. It's called depth-first search, or just DFS for short. And it's an algorithm that totally captures this idea of go deep first. Explore one option completely before you even think about looking at another.
All right, so let's really get into it. What does it actually mean to be depth first?
This quote really nails it. DFS is all about depth. It's laser-focused. It goes all in on one single path, exploring it to the absolute very end before it even glances at other options. It's kind of like this tenacious, single-minded approach to just exploring.
Okay, so mazes are a great starting point, a perfect analogy, really. But in the world of computer science, DFS is actually used on something called a graph. And hey, don't let the word graph throw you off. It's just a bunch of points, we call them nodes, that are connected by lines, which we call edges. And these things can represent pretty much anything, like a social network connecting you to your friends, or even a city's roadmap connecting all the intersections. So how does DFS actually navigate one of these graphs? Well, it follows a few really clear steps. First, it just starts at any old node. Doesn't matter which one. Then, step 2, it dives as deep as it can down one path. Now, this is crucial. As it goes, it marks every node as visited. That's how it avoids going in circles forever. When it finally hits a dead end, that's step 4, it just backtracks to the last place it had a choice and, you guessed it, explores a path that hasn't been down yet. And it just keeps doing this over and over until absolutely everything has been explored.
But wait, how does it remember where to backtrack to? This is the clever part. It uses something called a stack. And the best way to think of a stack is, well, like a stack of plates. You can only put a new plate on the top, and you can only take a plate off the top. DFS does the exact same thing, but with breadcrumbs. Every time it gets to a junction and has to make a choice, it drops a breadcrumb on top of the stack. When it hits a dead end, it just pops that top breadcrumb off to know exactly where its last choice was. Simple, right? Last one in is the first one out.
Okay, and to keep everything straight, DFS uses this really cool coloring system. Think of it like a traffic light for exploring. If a node is white, it means we haven't even seen it yet. It's totally new territory. If it's gray, that means we found it and we're currently exploring paths that lead out from it. It's on our active to-do list. And once a node is black, we're done with it. It's been fully explored, every single path has been checked. This whole system is basically the secret sauce that makes sure DFS is super efficient and never gets lost, going in circles.
Okay, so this is all a pretty neat idea, right? A cool thought exercise, but who cares? Why does any of this matter? Where do we actually use this maze-solving trick in the real world?
Oh man, you would be surprised. The applications are everywhere. I mean, for starters, it's amazing for solving puzzles like Sudoku, where you try one number and just follow that path to see if it works. It's also the backbone of something called topological sorting. Okay, think about building a house. You have to build the walls before you can put on the roof, right? There's an order to things. DFS is perfect for figuring out that exact sequence for any set of tasks that depend on each other. And it gets even cooler. In network analysis, it can find articulation points, which are basically critical weak spots that, if they failed, would split the entire network apart. But really, DFS is way more than just a collection of cool applications. It's a fundamental way of thinking about how to solve problems. And to really truly appreciate why it matters, you have to meet its famous counterpart. This is breadth first search, or BFS, and the comparison is perfect. If DFS is a deep-sea diver going all the way down one trench, BFS is more like a swimmer, checking out the entire surface of the water, level by level. So DFS is really space efficient. It's lean, you know? It only has to remember the path it's currently on. BFS, on the other hand, can be a bit of a memory hog because it has to keep track of a lot more nodes. But, and this is a big but, BFS gives you a rock-solid guarantee. It will always find the shortest path. So which one do you use? It totally depends on what you're trying to do.
And speaking of efficiency, you're going to see this funky-looking notation pop up when people talk about DFS. This is called Big O notation, and it's just a way for computer scientists to talk about how fast and efficient an algorithm is.
So what on earth does O of V plus E actually mean? Well, let's break it down. V just stands for vertices. Remember, those are the nodes or points. And E stands for edges, the connections between them. All this formula is really saying is that the time it takes to run DFS is basically tied to the number of things it has to look at. It touches every single node and every single edge exactly one time. That's it. No wasted effort. I mean, in the world of algorithms, you really can't get much more efficient than that. And this quote, this really gets to the heart of why DFS is so important. Its true power isn't just as a standalone tool. It's a fundamental building block. So many other, way more complex algorithms actually use DFS as a subroutine to get their own jobs done. You know, learning DFS is kind of like learning a power chord on a guitar. Once you know it, you can suddenly play a ton of different songs. So I want to leave you with this thought. The next time you're facing some big, complicated problem, just remember the maze. That simple idea, just go deep and then backtrack when you have to. It's not just a way to find your way out of a puzzle. It is a profoundly powerful way to solve problems, and it's beating at the very heart of our digital world. So what other complex problems out there could be cracked with just this simple, elegant approach?